This is Jack Jackson. We're going to continue our look at different classes of functions and some of their characteristics and how we can use our knowledge of derivatives to help explain some of these characteristics and maybe derive a few new ones. In this video, we're going to be talking about rational functions. Now, rational functions are fraction functions where the numerator and denominator are polynomial functions. They actually include the polynomial functions because you can just make the denominator be 1. And in fact, they have many characteristics in common with polynomial functions, but they also share some interesting properties that are not found in polynomial functions, at least in some of the examples. And here's a list of some of their basic characteristics. So they have their domain, this entire set of real numbers except for input values, which make the denominator equal to 0. And so, of course, there will be a finite number of those, and each of those roots of the denominator corresponds to a discontinuity in the function. There are two types of discontinuities that can happen. They're either a hole in the graph, a removable discontinuity, or a vertical asymptote. And we'll talk a little bit more about that as we go along here. If one of the factors of the denominator, if one factors the numerator and denominator, then you can easily identify inputs which are not in the domain. Anything that's going to make the denominator 0, make any one of the factors of the denominator 0, that will be something that's not in the domain. So do that first, and those are things that are not in the domain, and those are the x values. Say if x is your variable, those will be the x values where you have discontinuities. Now, if you're going to be able to tell asymptote from a hole in a graph, then what we can do is see if you can reduce the fraction then. If you reduce it and the x value still makes the denominator 0, then you get a vertical asymptote at that point, at that x value. On the other hand, if you reduce by canceling out like factors in the numerator and denominator, and the denominator is not 0 anymore when you put in the thing that made the original denominator 0, so it came from one of your canceled factors, then in fact put that x value in the numerator and denominator and you get an output out of the reduced version. That output is the y value of the hole in the graph. Okay, so that's how you can tell those apart from the formula. Now, between the discontinuities, the function is continuous and infinitely differentiable. So its shape is somewhat similar to a polynomial function, connected, smooth. Okay? And any linear factor of the numerator that's not a factor of the denominator corresponds to an x-intercept. So any x that makes one of those factors in the numerator 0, but not the denominator 0, then that's going to give you an x-intercept, x value of the x-intercept. Okay. Now the shape of the graph near those x-intercepts depends on the multiplicity of the roots, very similar to the way we did with polynomial functions in our previous video. So for example, an even multiplicity root, so if you have an x minus 3 squared or x minus 3 to the fourth in the numerator, it's going to touch the x-axis and turn around at that point. Say if it's x minus 4 squared, it's going to hit at 4, 0, it's going to hit the graph of the x-axis and turn around without going through to the other side. On the other hand, if it's an odd factor, it'll go through from one side to the other. If it's a multiplicity 1 root, a simple root, then it'll just go through more or less like a straight line. But if it's a multiplicity root bigger than 1, like multiplicity 3 or 5 root, it'll touch the x-axis and also be an inflection point there with a horizontal tangent line. The end behavior of the power function, of the polynomial function, can be found by just looking at the highest power term, what we call the leading term in the numerator and denominator. Ignore the rest, and that generates, the ratio of those generates a power function, and the end behavior will be the same as the end behavior of that power function. So specifically, if the degree of the numerator is larger than the degree of the denominator, then the function approaches positive or negative infinity as x approaches positive or negative infinity. If the degree of the numerator and denominator are the same, then the function has the same non-zero horizontal asymptote on both ends, both the far right and the far left, with a value equal to the ratio of those leading coefficients. And if the degree of the numerator is smaller than the degree of the denominator, then the function has a horizontal asymptote of the x-axis on both ends. So when the power is bigger on the bottom, you always have the x-axis as an asymptote. And if the power is bigger on the top, you don't have a horizontal asymptote. The power is the same on the top and the bottom, the biggest one, the degree. Then we get a horizontal asymptote that's not zero. Now, when you find the derivative, remember that you're using the quotient rule. So if it's a polynomial p of x over a polynomial q of x, that's a rational function. The derivative of that using the quotient rule is the bottom times the derivative of the top minus the top times the derivative of the bottom over the bottom squared, like that. And so notice that in particular, if you have something that's a factor of the denominator, it's still a factor in the denominator for the derivative. So any place that the original one is undefined, the derivative will be undefined there as well. Of course, that's always true for any function. And the numerator, notice that the degree is, well, what can we have here? We got the degree of q times 1 less than the degree of p, because remember the degree of p prime is 1 down for the degree of p. And similarly over here, q goes down 1. So this part here in the top has at most degree, whatever the degree is of q plus the degree of p, and then minus 1. Although sometimes it will, there'll be some cancellation there, and you'll get something of a smaller degree, but that would be the largest that it could be. Okay, so those are some basic characteristics. Now let's look at an example. Okay, so take this, use calculus, pre-calculus, and graphing technology to completely analyze and describe the following function. F of x equals, the numerator is x cubed plus x squared minus 8x minus 12 over the denominator of 2x squared minus 10x plus 12. So what you want to do this is clearly and carefully graph this using maybe some graphing technology. There's something like a computer program like Graphmatica or something like that, or your calculator graphing technology. Compute its first derivative, compute its second derivative, graph all three of those together. Go back and analyze things like tell me the domain, the range, the x and y intercepts, vertical asymptotes, horizontal asymptotes, holes in the graph, anything that might be kind of interesting about this function, try to find that out. So what I'd like you to do now is work on that yourself, and then come back and check your results with me as you go forward. So press pause now. Well, now that you're back, hopefully you've done this on your own. If you haven't, please go ahead and do that. But here's how we could enter in the calculator this particular thing. So this would be the first thing I might do here when I would be working on this, say, with the TI-84. So I put the original function just like it is in the calculator, like this. Now remember, a horizontal fraction line is both a division and a grouping symbol, whereas this division sign right here, or the little line with the two dots, is just a division sign only and not a grouping symbol. So you have to remember to put the entire numerator in parentheses and the entire denominator in parentheses. So be sure you enter it like this. Now I had to, a little trial and error, pick a window. So we might have started with, say, a zoom standard, and then see we needed to go out a little bit more to see some interesting things. And looks like from negative 33 to 33 for x and negative 13 to 22 for y seems to be at least one possible reasonable window. And looks like we see at least two pieces here, although there might be a hole in there or something. And we get some interesting things going on here. Just a quick glance at that. Looks like we have a minimum over here in the first quadrant, a maximum over here. I can't tell if that's hitting the x-axis or if it's in the second or third quadrant. We might need to zoom in closer there. Looks like it crosses the x-axis maybe once here. Looks like we may have a vertical asymptote. and so forth. When we do a quick table of it, we sort of stumble across x is 2 and x is 3 both giving us errors. And so if that's the case, those should be factors of the denominator here. Clearly we can factor out a 2, and then we're left with x squared minus 5x plus 6, which apparently factors as x minus 2 and x minus 3. So we could kind of check that out. And the denominator, we could work that out by FOIL and double check that. X times x is x squared. Negative 3 times negative 2 is 6. We get negative 3x minus 2x is negative 5x. So middle term, distribute the 2. We're back where we started in the denominator. So that did check out. Now, it turns out that in the numerator, one of the things you can see by looking at the graph is that at x equals 2, it looks like we have a vertical asymptote right there. But x equals 3 is just to the right of that. We do not have a vertical asymptote. So that indicates that must be a hole in the graph. To verify that algebraically, that means we should have x minus 3 as a factor in the numerator. To check that out, we could do a couple of different ways. We could just put the numerator in and put in x minus 3 and see that it works out to be, put in 3 as a x value and see that we get 0. And once we see that, we can check this and figure out the other factor by doing long division or maybe synthetic division. So here's the synthetic division. You write down the coefficients 1, 1, negative 8, and negative 12, and put the root of 3 out here. So that means we're dividing out by x minus 3. And we hope to see a 0 remainder, which is what we do get here. And the way synthetic division works is you take this 1 and bring it down. 3 times 1 is 3. 3 plus 1 is 4. 3 times 4 is 12. Negative 8 plus 12 is 4. 3 times 4 is 12. Negative 12 plus 12 is 0. This last part is the remainder. So since it's a remainder of 0, this says that this other part is the other factor, and this stands for 4 plus 4x plus 1x squared, or in decreasing order, x squared plus 4x plus 4. So if you multiply these two back out to check, you should get this one over here, so you can check that if you want. Now that one, hopefully you recognize, is a trinomial square. It's just x plus 2 squared. Square the first, you get x squared. Square the last, you get 4. And multiply these two together to get the middle term. So that works out nicely. And then we cancel what we can. We can cancel out. Okay, before we cancel out, notice that x equals 3 and x equals 2 are the things that are not in the domain. So the domain is all reals except for 3 and 2, which of course gave us error messages up here. We can also cancel out the negative 3 now, and it's equal to this, provided x is not 3. If you plug in 3 to this, which you can see the details worked out here, 3 plus 2 is 5 squared is 25, 3 minus 2 is 1 times 2 is 2, you get 25 halves, or 12.5. So we can check that in our calculator down here by putting in the reduced version, which is what I have here for y2. Notice that that agrees exactly with y1, so we see that our factoring was done correctly. And I said it agrees exactly, but it does not agree at 3. At 3, we have an error in the original one, dividing by 0, 0 over 0 when you plug in. But whereas in the reduced version, without that, if we plug in 3, we get 12.5. So that means that the point 3, 12.5 is a hole in the graph, a removable discontinuity. In other words, the limit as x approaches 3 of this function is 12.5, or 25 halves. But the function is actually undefined there, so that's called a hole in the graph or removable discontinuity. Now, we can kind of work with this reduced version if we want, or with the original version as we go forward, because for everywhere except for that hole, they're exactly the same. Now, what about x-intercepts? That would be when the numerator is 0, but the denominator is not. So 3 is not an x-intercept because it's undefined at 3. 3, 12.5 is a hole in the graph. But x equals negative 2 is a place which makes the numerator 0 and denominator something else. So when you plug in x equals negative 2, you get a y of 0. And so that is a that's going to be an x-intercept the only time it crosses the x-axis. And in fact, that's a multiplicity 2 root because of the 2 up here. So we should see that that's also an extremum, either a local maximum or local minimum. In fact, it's a local maximum. So this graph actually comes up here, touches exactly at -2, 0, and then turns around and comes back down. This piece is one solid piece. This piece up here is actually two pieces. Comes as vertical asymptote here, hole in the graph, and then keeps continuing on. So the graph is a total of 3 pieces altogether. Now, what about minima and maxima? The minima and maxima occur at these 2 points right here. You can do a calc minimum or calc maximum, and if you look at calc minimum, well, it at least approximately is 6/8 for the minimum, and we know there's a maximum at -2, 0. Now we can verify these algebraically by looking at derivatives. So let's do some derivatives. Now, I'm going to use the reduced version, but remember we have to go ahead and put that x is not equal to 3 all the way down. So x is not equal to 3 in the original, nor is it equal to 3 in any of the derivatives. So they all have hole in a graph at x equals 3. Both the first derivative, second derivative, third, fourth, fifth derivatives, whatever, and the original function. So this 1/2 here is a constant, so I can factor it out. And then we can use the quotient rule. Bottom, x minus 2, times the derivative of the top, minus the top times the derivative of the bottom, or the bottom square. So the bottom is x minus 2, so I factored out the 1/2. So it's x minus 2 squared in the denominator. Bottom is x minus 2. The derivative of the top would be, this is like u squared. So it's 2u to the first times the derivative of the u. The derivative of x plus 2 is just 1. So there we have the bottom times the derivative of the top. Minus the top, x plus 2 squared, times the derivative of the bottom. The 2 is already out of the way, remember. And we have the derivative of x minus 2, which is just 1. So let's see what we can do here. Looks like both of these have an x plus 2, which I can factor out. Leaves me the 2 times 1 is 2, times x minus 2, which is 2x minus 4. And then here we have, well, just -1 times x plus 2 to the first power, which is -x minus 2. Continuing on, we can combine some like terms here. 2x minus x is x. -4 minus 2 is -6. And we still have our x plus 2 here and x minus 2 squared, and I went ahead and put the 2 back in the denominator. And this is what it turns out to be. Had we worked with the original one and worked out the derivative and then factored it, we would get the same thing here, but we would have an x minus 3 in the numerator and the denominator. Or maybe that squared, possibly, which is the same thing. Okay, so we could graph that. We could just graph this one here without the x, and just put the hole at x equals 3. Plug in 3 for this to get the y value of that hole. Or in Graphmatica, for example, we could put in this version right here, and the hole would show up. Okay, now how about a second derivative? Well, I'm going to go ahead and multiply this out because it's going to make it a little bit easier on me. I'm going to factor out the 1/2. And then constant multiple rules, and then it says that you got the derivative of what's left. Well, what's left in the top doing FOIL, distributive property is x squared, let's see, -6x plus 2x is -4x, 2 times -6 is -12. And the bottom, I'm going to just leave it x minus 2 squared. Now we're going to use the quotient rule, so we still have the 1/2 out front from the constant multiple rule. So it's the bottom times derivative of the top. Derivative of the top is 2x minus 4 plus 0. Minus the top, there we go, times the derivative of the bottom, which is 2, it's u squared, so it's 2u du. So it's 2 times x minus 2 times the derivative of x minus 2, which is 1. Okay, so let's see here. I'm going to notice that I have an x minus 2 here and an x minus 2 here. I'm going to factor that out front. Oh, by the way, in the bottom, you have the bottom squared. Let me go ahead and do that. So x minus 2 squared, multiply the exponents, that becomes 4 for the power there. However, as is typical in these cases, even though this starts out 4th power, we're going to get an x minus 2 here and here, so it's going to end up just only going up 1 power from 2 to 3 here, and that's pretty usual for that to happen. So let's see what's going on here. So we factor out an x minus 2. What's left? The other x minus 2 times 2x minus 4. And here we have just 2, make it negative 2 times this trinomial. Distribute here, we get negative 2x squared plus 8x plus 24. Here we distribute using FOIL, and we get 2x squared, let's see, we get minus 8 plus 8, negative 2 times negative 4 is positive 8. And here we get negative 4x minus 4x is negative 8x. Now this x minus 2 here is a factor of the whole denominator. Notice the parentheses here. And so it will cancel with one of these in the bottom, bringing that down to the third power. Combined like terms, the x squared terms go away and the x terms go away. So you just get 8 plus 24 is 32. 32 and 2 cancel down to 16. And so our second derivative reduces finally to just 16 over x minus 2 cubed, again, where x is not equal to 3. Or if you don't want to put the x is not equal to 3, then it's 16 times x minus 3 over x minus 2 cubed over x minus 3. Alright, now let's see what, now that we have these formulas, let's look at the formulas and see what they tell us about the original function. In particular, we're interested when the derivative is equal to 0. Okay? Well, as usual, you see that the derivative is undefined when x equals 3. That's going to be a hole in the graph on the derivative and the original function. Again, x equals 2 is going to make the denominator 0, so the derivative has a vertical asymptote at x equals 2, just like the original function did. And this is typical of any function, so anytime you have a function which has a vertical asymptote, its derivative will also have a vertical asymptote at the same x value. Continuing on, what makes the numerator 0? Well, negative 2 and positive 6. And those should be places where the original function has extrema. If you plug in negative 2 in the original function here, notice you get 0 divided by something else that's not 0. So you get 0 here. So negative 2, 0 is a local extremum. And if you plug in 6 here, you get 6 plus 2 is 8. Square, that's 64. 8 minus 2 is 4. 4 times 2 is 8. 64 divided by 8, that's 8. So 6, 8 is also local extremum. And if you look, we kind of already knew that from the calc min and calc max. Well, at least we knew it was approximately 6, 8. In fact, it's exactly 6, 8 for that minimum. And we knew by the multiplicities of the roots there, we saw that this algebra that was going to happen down here is going to be what's going to make this be a maximum at negative 2, 0. Now, how about the inflection points? Does it have any, or where are they? Well, if you look at the second derivative, it's never equal to 0. Notice when x is less than x is less than 2, this is a negative to odd power is negative, and 16 is positive, so this is negative. So to the left of 2, the original graph is concave down, which you can see from the picture here. To the left of this vertical asymptote, which is at x equals 2, the original graph is all concave down. And to the right of that, the original graph is all concave up. And of course we see that because if x is bigger than 2, x minus 2 is positive, cubit is positive, positive divided by positive is positive. Now here is a Graphmatica graph, and I graph these in Graphmatica using the versions that have the x minus 3's in them, remembering to put parentheses around the numerator and parentheses around the denominator, and we get these. So the blue graph is the original graph, and notice you can see the hole in the graph right here, and that was at, where was it, 3, 12.5. And at 3 something up here, we have a hole in the graph on the, that's the second derivative, and the red one is the first derivative, has a hole in the graph right there. So the first derivative is here in red, second derivative is in green. Original functions in blue. So notice that the second derivative, let's look at the first derivative. First derivative hits the x-axis right here, and that's where the original function has a local maximum, negative 2. Second derivative first derivative hits the x-axis right here at, I believe it was 6, wasn't it? Yes, 6. and the original function has a local minimum there at 6, 8 right there. The second derivative, well, you can see some characteristics of the first derivative first. First derivative starts out positive, meaning the original function is going to be increasing. It hits the x-axis here at -2, so we have a local maximum there of the original function. And then the first derivative goes negative, which means that the original function must be decreasing there. Over here, the first derivative is negative, so the original function is decreasing. Over here, the first derivative is positive, so the original function is increasing. Where the x crosses the x-axis on the first derivative is where you have a minimum or a maximum on the original function. The second derivative, then, of course, being the derivative of the first derivative, ends up telling us about increasing and decreasing on the first derivative, and it tells us about concavity on the original function. So notice over here, and for this part that's over here to the right of 2, that's going to be all positive, so the original function is all concave up, and the first derivative is all increasing with a hole in it, of course. Over here, to the left of x equals 2, the second derivative is all negative. It's actually below the x-axis here. It's kind of green here, kind of has an asymptote here and here. And that's all negative, so the first derivative is decreasing, which you see in red, and the original function is all concave down. So we see the range. Actually, what's the range? Well, if you look, this goes forever down, this goes forever up, but there's a break here in the middle from 0 to 8. So it's from negative infinity up to 0, and that duplicates some of that. And then it goes from 8 to infinity. Now, it would skip over 12.5 right here, but it actually picks up 12.5 over here somewhere. So it actually does pick up all those values from 8 on up to infinity as well. Concave down to the left of the vertical asymptote at x equals 3, concave up to the right of x equals 2, that should say. And the function is increasing from negative infinity to -2, and from x going from 6 to infinity, and decreasing from -2 to 2, 2 to 3, and 3 to 6. Since the degree of the numerator is 1 larger than the degree of the denominator, we should expect it to look like a linear power function. So if you go back to the very original one, or way back here, and you just do x cubed over 2x squared, that reduces to 1/2 x. So it should look a lot like a line 1/2 x. Actually, it looks like 1/2 x plus some constant, and that gives you this slanted or oblique asymptote. How do we find exactly what that function is that it's approaching on the edges? The end behavior, so-called end behavior. Well, we do that by long division. I can do it with the original function, but I can also do it with the reduced version. Somewhere I multiplied, yeah, here I kind of multiplied out this is x squared minus 4x minus 12, and I can multiply the bottom as x squared minus 4x plus 4. And so those are the things that I want to, let's see, is that what I want to divide out? No. The reduced version is right here, excuse me. The reduced version, I've got 2x minus 4 for the denominator, and the top I've got x squared plus 4x plus 4. So that's what I want to divide out. So I take the numerator, x squared plus 4x plus 4. The denominator is 2x minus 4. And just do what we call long division. So we do x squared divided by 2x is 1/2 x. So notice when you multiply 1/2 x times 2x, the 1/2 times 2 is 1. X times x is x squared. These are exactly opposite, exactly the same. Then I multiply 1/2 x times -4. 1/2 times -4 is -2. X times 4 gives us an x. And line these up with the corresponding parts here, or sort of lined up here. And then add up like terms. Well, subtract, actually. So when I subtract, I change the signs and add. Notice that I have the change signs in these little boxes. and the original signs are down here. So that way, if I need to look back at this, I can tell what was original and what was changed. So when I multiply 1/2 x times 2x minus 4, I get positive x squared minus 2x. But when I subtract, I'm changing the sign, so now I'm adding negative x squared plus 2x. So that makes this cancel out completely, and that's what you want to choose. You want to choose the right thing at the top, so this first term goes out completely. Now, what does that force the rest of it to happen? Well, 4x plus a positive 2x is 6x. Of course, we still have a 4 from here. Now we take 6x divided by 2x, that's 3. 3 times 2x is 6x. 3 times negative 4 is negative 12. Change the signs to negative, positive, and add, so these cancel out on the 6x's. And we got 4x plus 12x is 16. So, what we're saying is another way to write it, another way to write the original function is 1/2 x plus 3 plus 16 over 2x minus 4. Actually, that even reduces. So you could say 1/2 x plus 3 plus 8 over x minus 2. And you could write it that way. Now notice as x goes to infinity, that fraction part, the 16 over 2x minus 4, goes to 0. And the graph approaches this horizontal, not horizontal, but slanted asymptote or oblique asymptote of 1/2 x plus 3. So if I graph it with that, there's the asymptote graph, and you can see that graphically that works out. Now this particular example gave you lots of different techniques, algebraic techniques, graphical techniques, calculus techniques to review, and certainly technology techniques. We combine these together. We get to review things like synthetic division, long division, quotient rule, for example, on derivatives, of course the chain rule. We also looked at graphing. We looked at hole in the graph, vertical asymptote. We got to talk about x and y intercepts, okay, and so forth. So this example reviews a lot of things about this. Now, what I want to do at this point is refer you to some of my algebra videos on rational functions, where I go over many more examples of rational functions. Now there, of course, I don't compute derivatives, but you might pause the videos there and actually compute derivatives as well to explain why I get some of the things that I get in those examples. And I do several examples showing you some interesting things that may come up. So I refer you to my rational functions section of my algebra videos for more background detail and several more examples.